The next part of our course is called boundary conditions. You know that setting boundary conditions for Navier-Stokes equations is not a trivial task. From a theoretical point of view, it is one of the most difficult part of our lessons. At the first sight, it seems that from the point of view of space variables, we deal with a typical boundary value problem. And for its decision, it is necessary to set all gas dynamic parameters on all the boundary of the estimated area. Actually, it is not so. Let's consider, as an example, a compressible gas flow along an axis x with speed u from left to right. As it was mentioned above, any point of the flow can propagate its inflows on the surrounding space as follows. First, with speed u, due to the moment of the flow, so it's down the flow. With speed u plus a, the speed of sound, due to the movement of the flow and propagation of sound vibrations, also down the flow. And next influence is with speed u minus speed of sound, due to the propagation of sound vibrations. If speed u exceeds the speed of sounds, there is no upwind influence. But if speed u is less than speed of sound, it propagates upwind the flow. Thus, in case of a supersonic flow from the left to right, the right boundary of an estimated arrow can't influence up the flow in any way, and setting boundary conditions on it contradicts any physical sense. If speed at the exit from the unestimated area is subsonic, then extension of influence up the flow is possible, owing to propagation of sound vibrations, and it is required to set boundary conditions on this boundary. The question is, what boundary conditions are needed to be set on various types of boundary of an estimated area? The answer to this question is connected with so-called characteristics. And so the next paragraph is called characteristics, and also Riemann's invariants. It is supposed that on the boundaries of a computational domain, it is possible to neglect the influence of viscosity. This assumption is fair for many types of boundaries, except for cases when a boundary is a wall or a plane of symmetry or line of symmetry. We will examine this boundary and symmetry later. The Euler equations are a set of quasi-linear hyperbolic equations governing adiabatic and inviscid flow. Consider the following unsteady homogeneous hyperbolic equation. Что ж такое-то? Странно. Shift-V. Чего же он не рисует-то, блядь? Ёб твою мать. Да что-то мне эта херня не работает. Вот, заработал. С этого момента, а так надо вырезать. Итак, so consider the following unsteady homogeneous hyperbolic equation. du by dt plus a of u du by dx is equal to 0. And we have the initial conditions. U of 0 x is equal to phi of x. X is between minus infinity and plus infinity. Characteristics are the curves in xt plane determined by the equation d x of t by dt is equal to a of u, and u is of t and x of t. So we have the function of x of t in this equation. If the solution u of tx is differentiable, then it remains constant along the characteristic x of t. We can see that the derivative of u with respect to t, it's the function of t and x of t. So we can, and the derivative is the following: the du by dt plus du by dx and dx of t by t. It is equal du by dt plus a of u from this du by dx, and this expression is the same as this, and it is equal to 0. So I repeat, the solution u is constant along the characteristic x of t. Now let's consider a one-dimensional non-stationary problem of a compressed inviscid gas along the axis x. The main equation in this case are as follows. In conservative form, the equation of mass d rho by dt plus d by dx of rho u, the equation of momentum in x direction, and energy equation. Here, as you remember, E, capital E, is total energy. As I told you, it is a so-called conservative form of the equations. The other form is obtained by subtracting the continuity equation from the second and the third equations of system and multiplied by u and t respectively. So we have the following form of the same equation: the continuity equation, the momentum equation, and energy equation. If the gas is calorically perfect, the total energy E can be expressed through pressure and speed by the following formula. Capital E, the total energy, is equal to internal energy plus 1/2 of u to the second power. If we use the formula for internal energy, P pressure by beta, rho plus this one, kinetic energy. Here B beta is equal to specific heat ratio gamma minus 1. So that we have the following formula for differential of total energy. dE is equal to dP over beta rho minus P d rho over beta rho to the second power plus u du. Substituting this equation in the third equation, or energy equation, we obtain the following formula. From here, considering the continuity and momentum equation, we receive the energy equation through pressure. It has the following form: dp by dt plus gamma p du by dx plus u dp by dx. Thus, we can solve the considered equation in unknown vector w. W is equal to the vector which consists of rho density u and p. It consists of three unknown scalars. And the system of equation in a vector form is as follows: dw by dt plus a dw by dx is equal to the 0. When we analyze the equation of continuity, momentum and energy in the previous above form, we have the following formula for A. A is equal to the following matrix: first row u, row 0, 0 u, 1 identity over rho, and the third row is gamma p u. The eigenvalues of this matrix A are equal to lambda 1 is equal to u, lambda 2 is equal to u minus a, the speed of sound, and lambda 3 is equal to u plus a. And we can build the corresponding eigenvalues. For the first eigenvalue, lambda is equal to u, we have the following: vector. For these eigenvalues, we have this eigenvalue, and for eigenvalue u plus a, we have this eigenvalue, rho over a, 1 rho a. Thus, in similarly transformation, we know this in transformation, matrix A is introduced in the following formula. The inverse of matrix S, diagonal matrix lambda, multiplied by matrix S. Here we have the following formulas for inverse of S and for matrix S itself. You see that matrix S to the -1 power is composed of eigenvectors. Please compare this equation and this. And matrix S is found as the inverse for it for S minus 1. Considering this equation, the vector equation which we had can be transformed in so-called characteristic form. S dw by dt plus lambda. I should say that lambda is the diagonal matrix which consists of eigenvalues. Lambda 1, lambda 2 and lambda 3. Then S matrix S and dw by dx. Let us define the characteristic variables. Xi. The vector xi consists of xi1, xi2 and xi3 and is defined, this vector, as follows. d xi is equal to s and differential of double u. So it's this part of equation. And we get the characteristic form of the governing equation d xi plus diagonal matrix lambda multiplied by d xi by dx. This equation is also called characteristic form of the governing equations and has the advantage of decoupling the characteristic variables. So we can separate this equation into three scalar equations. Each characteristic equation within this can be written as follows: d xi by dt plus lambda sub I d psi I by dx is equal to 0. We remember that the vector xi, its differential is equal to matrix S multiplied by d vector W. And so we can multiply the matrix S and vector the differential of our vector W. If we do it, we get the vector d psi in the following form. The first row of this vector equals d rho minus dp over a to the second power. The second row is equal to du over 2 minus dp over 2 rho a. And the third row du, 1/2 of du plus dp over 2 rho a. The main difference in the sign. Here you can see minus and here plus. And so we have the following characteristics. First differential d psi 1, which is commonly written in the following d psi 0, is equal to dp minus dp d rho minus dp by u2. And as we will see, it is equal to the differential of entropy S. The second characteristic is often written in the following form: d psi minus is equal to du minus dp over rho u. And the third characteristic, which is defined as d psi plus, is written in this form. As I told you, S is an entropy and A is a speed of sound. Notice that characteristic variables are strictly conserved during their propagations along the characteristics. That is, the quantity psi sub I, which satisfies the equation 519. This equation, I mean. Remains constant along the characteristic C sub I, which is defined by the following expression: d xi of t by t is equal to lambda sub I. Since along this characteristic Ci, the following expression is true: d xi I by dt, the full derivative of psi is equal to d psi by dt plus d psi I by dx multiplied by dx by dt, and it is equal to the characteristic equation, which, as we know from 5.19, is equal to 0. So this characteristic, this value, is constant along the characteristic. I repeat that it is constant. The variables psi I, which we defined, are also called Riemann variables or Riemann's invariants when they remain constant. The system of equation in characteristic form can also be written as follows. The first equation the second equation and the third, with the following definitions of three characteristics. On the first characteristic C0, in the plane xt, this characteristic is defined, this C0 is defined by the following formula: dx by dt is equal to u. On the characteristic C plus, we have the following formula: dx by dt is equal to u plus a, speed of sound. And on characteristic C minus, we have dx by dt, which is equal to u minus a. Note that these lines, I mean characteristic lines, are not rectilinear, since lambda I may be variable during the solution. We can write this characteristic C0, it is this line, and as you remember, it defined by dx by dt is equal to u. This is C plus characteristic, and C minus characteristic, which is defined by the differential equation dx by dt is equal to u minus c. I repeat that, of course, c and u are variable, and so these lines are not rectilinear. It is of interest also to notice that the first characteristic equation expresses the constant transport of entropy S along the path line dx by dt equivalent to u. Let us discuss this problem. As we know, the following is true for isentropic processes. P, pressure, is equal to some constant k multiplied by rho to the power gamma. It is true for isentropic processes. Let's take the differential of P and we have the following formula. dP is equal to A to the second power d rho. For isentropic process, we have the following dP. D rho minus 1 over A to the second power dP is equal to 0 because dP is equal to this. We know that it is the formula of the first or zero characteristic C0, and so we can write that it's true for entropy D on the zero characteristic of D of S of entropy is equal to 0 along the characteristic which is defined along the line dx by dt is equal to u. Thus, the entropy propagates along the path line and it's conserved along this characteristic as long as discontinuous do not appear. I mean some both and maybe viscosity. For the isentropic flows, the Riemann or characteristic variables can be integrated as follows for either C plus and C minus. For example, for characteristic C plus, we have the following: xi plus is equal to u integral of dp over d rho. If we express by the isentropic relations dp, we can rewrite this equation in the following form: u plus integral of speed of sound d rho over rho. We used the following expressions for this formula. We remember that k is the constant. This gives us the following formula: xi u is equal to u plus, after integration we get this formula, xi plus is equal to u plus 2 over gamma minus 1 multiplied by a, the speed of sound. And similarly, we can receive the formula for xi minus. And so we have the formulas for all characteristic for xi 0, xi plus, and xi minus. In the literature, another notation of the invariance is often used. R0 is equal to psi0 and is equal to entropy. R plus, which is equal to psi plus, and is equal to u plus 2 over gamma minus 1 a, and R minus, which is equal to psi minus and is equal to u minus 2 over gamma minus 1 a. One can interpret the physical state at a given point in a one-dimensional isentropic inviscid flow as a resultant from the quantities transported along the characteristics. Let us examine this problem. At a given point P in the plane x, t, which is shown on this figure, the physical flow condition will be determined by the entropy transported from C along C0 at speed u, that is, along the streamline. The velocity u and the pressure or the density are determined from the quantities u plus minus 2a over gamma minus 1, and they are transported at velocity u plus minus a along the characteristics c plus and c minus. Hence, if we compare the points P and these points, we have the following expressions. For P and P plus, this expression is true. The R plus or psi plus characteristic remains the same. For characteristic C minus or psi minus, we have the constant value of this characteristic, and so in points P minus and P, the following expressions are the same. And for characteristic 0, psi 0, we have the constant entropy. I repeat this. So the plus C plus remain the same in the point. The characteristic psi plus, sorry, is the same in the point P and P plus. The di2 is the same in the point P and P minus. And the 0 characteristic psi or R0, it's true that it is the same in the points P and P0. we may see that there is the difference between these pictures when we have supersonic flow and subsonic flow. We may see that the influence goes here from left to right, all influence, and in subsonic flow we have the influence of C minus characteristic from right to left, so upwind. Each point P in the plane xt is reached by one characteristics of each type, and therefore the flow situation at a given position x at the time t is solely dependent on the domains between p plus and p minus. This is the domain of dependence of p. Inversely, referring to figure which we discussed, the region included between the characteristic issuing from p forms the domain of inflows of p. This is the physical region of dependence. So these points which are in this physical region depend on the flow in the point P. The considered problem is easily generalized to three-dimensional case. It is easy to show that in this case there appear two more characteristics determined by equation dx of t by dt equaling u. And the corresponding Riemann's invariants are the following. R4 is equal to V, and R fifths is equal to W. You remember that U, V and W are the components of velocity.